is you have some sort of like specification, and this can be either formal, like a mathematical formula, or it can be something informal, like an input-output example. Then you throw this to your program synthesizer, and then the program synthesizer will actually find you a program that will satisfy your specification. So more formally, this is kind of like you're solving this exist for all formula, where you want to find the program P that for all inputs of that program, you will actually satisfy your specification. Right? So let's see some examples of what is actually happening in practice. And in these examples, I'll mostly focus on actually input-output specifications, because even though they are actually not precise, they're very easy for the users to actually provide this information. So like if you actually want to help people that don't know how to code, they probably will also do not know how to write a very complex mathematical formula that will describe their program, right? But they know how to give an example. So this is actually something that is used in Excel. So the idea is, let's say this would be columns in Excel, and you have your email address, and here is very nicely formatted. It's like first name dot last name at your email address, and you actually wanted to extract the first name. So what you can do is that you can provide, let's say, a few examples, and then you can press a button in Excel or drag, or there's like a button called flash fill, and then the rest gets filled for you. But on the back end, what's actually happening is program synthesis. So the idea is there's like this sort of like they're trying to find out what was your logic that you used to find the first two, and then they're going to find the program. And yes.
Just in this example, there needed to be some discussion, so to speak, with the user, some feedback. What about the other case, if the email is not in this format or something like that? Yeah,
so what happens if it's, then this output can be something that is random, right? Or is noisy. So since this is under specification, there's no guarantees that the solution is actually the one the user wants, right? And of course, if not all of them have the same format, then definitely you're going to have issues.
Perhaps your program would, or your synthesis should also output, I have my program as the following, just the following. It assumes the input is all this is, can we do it, or is it
so there's like some issues with HCI, right? How you actually convey that this is the correct program, right? Or there's like some work on maybe then, let's say if you figure out that most of them look okay, but some of them look suspicious, then you could say, okay, is this one actually correct? Because I'm quite not sure. Of course, how you determine those could be a bit more tricky, right? Here, you're assuming that everything is nicely formatted and everything works out, but it could be the case in practice, it doesn't work, right? But which is a limitation of this work. I mean, they have that limitation. Like if now you didn't actually have this nicely formatted, maybe here the first name is actually not the first name, it's something else. Because this is just your best guess to try to do this. But this is actually a feature that's in Excel since 2013 and is very useful for users. And at Excel, they actually, at Microsoft Research, they actually have a team dedicated just for program synthesis and trying to improve this technology so that it actually can go to production, right? And I think in 2016, the new Excel also has some improvements over this. So other things that I personally work on that also does program synthesis could be like, well, you're not working with strings anymore, but maybe you're working with tables, right? Like everyone has a lot of data. I did some experiments. I ran some solvers. Now I have tons of data. I have a lot of tables maybe. And now like, well, I need to do some analysis, right? Maybe I need to join my tables. Maybe I actually then need to do some averages. And if I know how to do that, maybe I'll write some scripts, right? But if you don't know how to do that, it can be very painful. Especially, so there's other people that now we're actually trying to help, like biologists. They have a lot of data, but they really don't know how to actually like do SQL queries or to actually extract the information they want from this. But again, they kind of know what they want at the end. So if giving a small example, they're like, well, if I have this example, I have some names, months, and some rates. I know I want to do some group bys per name, and then I want to do some averages over that, right? So maybe for this small example, I can manually do it. But then for, let's say, then I have a table with thousands of entries. I don't want to do that manually, right? So can you give this as an input? And then can this tool give you the output of a code that will not only work for this input-output example, but will also work for like a larger example, right? And this, here we were doing it for R. So R is kind of like a language that helps like for statistical studies. So you can do analyze there, and they have some sort of language there. So we're creating R scripts that then you could apply for this input, and then you have the output. So this was like some work I did for PLVI last year. And basically giving this, our tool will give you like kind of like this. So it's kind of like straight line code, so there's no conditionals, there's no loops. So you may think, okay, it's not very impressive, but even like these operations are actually hard for users, right? So even though it only has a few lines of code, sometimes users may spend like hours actually figuring out this. So this is just another example. So if you actually want to do like work with languages like Java, and you want to do synthesis in Java, so I have another work I also did last year. And here the idea was, again, from input-output example. So you have some libraries, and maybe I don't know how to operate with this library, maybe it's very complex, and I don't want to spend time reading all the Java doc of the library. I just want to know, like, if this library can do whatever I want, I just want to press a button and say go. So in this case, let's say I was operating over dates, but I don't really know how dates is implemented in Java, but I know how to express them in strings. So let's say if I have a date like this, and this is the format of the date, I just want you to extract the 13. Of course, maybe this is not the best example because you could also do like string operations over this, but imagine that you can actually ask more complex iterations. So the idea here is that giving this test case and the signature of the method, you throw this to a tool, and the tool will find you a sequence of API calls that actually will output you 13.
Always output 13?
Huh?
Always output 13?
Oh, well, for this input case, for this test case. Of course, to be honest, like you should have more than one test case, right? If you only have one test case, it's very likely that I'll find another program that throws 13 and is not really the one you want, right? So I would recommend you to have a few more than one example, but for here, for slide purpose, I only have one. But usually, even if you have only like 3 examples, you tend to have the solution you actually want to. Depending, like if you're returning a Boolean, probably need like maybe like 5 or more, because it's very easy to return true or false randomly and guess. Well, not in SAT, but we have millions of variables. So here, this is actually a real tool, and this is actually quite a stable tool that actually is written in Java, actually uses FOJ, and has some SAT encodings underneath, etc. So it's actually using SAT technology. And in this case, we'll actually find like you will build this data time formatter, and has this local date. We'll parse it. We'll get the day of the month, and then we'll return that day. So as you can see, it's actually creating objects that were never there, right? That were not in the input. So it can actually be fairly complex to know that, well, I have no idea about this library, and I have to find this sequence of API calls to use it. So I think this is actually could be useful for people. And if you want to try it, this is actually quite stable, so you can try it. And I'll have a new version even this month. But in this talk, so overall, I'll just say that program synthesis has many applications. Like in data science, I have some projects where we're trying to help like extract data, clean data, and then analyze the data. For SQL queries, for example, you can actually use users there. For problem repair, security, computer education, and many others. So it's a very hot topic right now. And there's a lot of research going on. So how do these tools actually work? Since you may not be very familiar. So I would say there are like 3 main classes I will categorize that. Of course, you can mix them. But the idea is that, of course, you can do enumerative search. So I'm searching for a program that will work, right? I could try all possible programs within my language, and eventually I'll get there. Of course, this will take a very long time because it's a very large search space, right? Yeah.
Why can't you just, if input equals to the given case, output?
Yeah, so the problem of that would be like, for starters, actually all the work I'm doing here doesn't even have conditionals. So it's conditional free and loop free. So it's a restricted form. But the idea, if you do that, that program would only work for that input.
Yeah, but how would you distinguish? Why isn't it a solution? How do you specify?
Yeah.
This is not a solution. You have something kind of a most general unifier. The program is most general.
Yeah, so usually people that work with conditionals, they're trying to have a solution that's more general. Like maybe you can express generality of saying, I want to use the minimal conditionals as possible to actually solve this problem, right? That's a different problem how you actually express generality versus the very thing that only works for this example, right? And it's a hard problem itself. So in this case, since I'm actually only working on things that don't have conditionals, all my solutions cannot be just like if this, if that, which is nice, so I don't have that problem. But the downside is that I'm actually cannot solve problems that require ifs, right? But even solving problems that don't require ifs is already quite challenging, right? But definitely that's something that I'll need to address at some point. So one way to prune the search space is that, well, maybe I can do some logical reasoning over my program, and maybe I can prune some infeasible programs, and so I don't need to search for entire search space, right?
Yeah. I think it's fine in your setting.
You can, yeah, you can generate, well, the program is guaranteed to pass all your test cases, of course, but it may not be the correct program, of course, yeah. Or it could be too specialized and only work for that one. I mean, that's a problem of under-specifying your specification, right? If you only use input-output examples, you're only guaranteeing that that passes, right? But is that strong enough? So if you require a stronger specification, you could have a stronger specification, right? So this will still work, all of the things that I'm describing here. Another approach that is very trendy right now is, of course, to use stochastic search. And so this is real codes. You could train a machine learning algorithm on a large corpora, and maybe someone already coded that. Maybe you can actually learn some patterns. So you could actually find this program quicker. And in the last, like, especially 2 years, a lot of works have only been doing just machine learning, which was with some impressive results, actually. So I claim that all these approaches have a common shortcoming, and that they kind of don't learn. So in the sense that, let's say during search, I found something, and this didn't actually pass my input-output example. Like, could I actually learn that if this problem doesn't work, other problems will not work as well, right? So could I actually learn from past mistakes? Of course, this is inspired by sat solving because of my background, but and this is this talk is going to be about. Yeah.
What has Sages been used?
Counter-guided, like the series approach to yes, but I mean they don't actually learn from. If you actually fail completely, it's a bit different there. Of course, you have a refinement loop,
Yes.
where you can actually learn. You can refine your formula, right? But it's a bit different learning here. So I was trying to do something a bit more. Can you generalize that counterexample, basically? Yeah, so learning from mistakes in this case of programs, the idea would be, well, let's say I'm operating over lists, and I have a list 1, 2, 3, and then a list 1, 2, and I'm doing map over this list directly, and let's say this was my program. And of course, then I would need to have some functions over the map, but it doesn't really matter what I'm going to map this list, which function I'm going to use is not going to work if I do just map x, right? And the reason is that because after I apply map, the size of the list is still the same. And here the size decreased, right? So more generally, what I want to say is that any function that applies directly over the input and preserves or increases the size of the list is not going to be a solution, right? So what I wanted to learn is kind of like, okay, I try map over this list, did not work. Can I prune all these other programs like reversing the list or sorting the list so I don't need to export them afterwards, right? And this comes like from sat solving. So my idea was, well, sat solvings are kind of like doing a search exploration, right? And they're trying variables. So instead of trying variables, maybe I could try something else. And they're checking conflicts and they're learning. So how can we go from this to synthesis? So this is this framework that was presented this summer at PLDI 2018. We call it conflict-driven synthesis. And the idea is that it kind of mimics the same framework where we have a search engine where we choose a component, and then we will have a partial program, and we'll check with something similar to unipropagation that if there's a feasible completion or not. And then if there's not, there's the conflict, and we try to learn something, and we backtrack, and so on, until either we have a synthesized program or we have no solution. So how can we do this in this context? So I'm going to use this running example, and this was before the World Cup. So I was like, well, soccer is a good thing, maybe Portugal will do well. But but it could be something else, yeah. So this is like, so the idea is that you want to compute the scores of the best K teams of a soccer league. So you have this function compute K sum, has the input of a list in an integer, and you want to output the sum of the two highest numbers, basically. So, oops, yeah. So the idea is that, okay, how do I solve this? Of course, to solve this, you have to have some sort of like domain, right? Like, what is my search space? So it's very common in a lot of synthesis problems that you have this domain-specific language that you're trying to search over it, right? So here, throughout this talk, I'll use this very small domain-specific language, but of course, you can increase this to be much more complex. So in this case, we have some operators that return you an integer, and this can be constants, like say 0 to 10. So we are finitizing them here. There can be the input. It could be like some operators over lists, like the last, had, some, maximum, or minimum. That will operate over the list and return you this integer value, right? Then you can have other components that operate over lists themselves and return you a list. So we'll take you the first n elements of a list, so return you that sublist. A filter we'll filter the list according to some predicates, and these predicates could be greater or equal than 0, less or equal than 0, or equal to 0. Then you can have this sort function or reverse function that will just sort the list or reverse the list. And you can have a list as an input of your system as well. So let's say if you only have this, how would I actually solve this problem, right, if I was doing it manually? So I would first sort it, and my sorting is very basic here, so it doesn't actually have any other parameter. So it only sorts in ascending order. Since I actually wanted to sort in reverse order, in a descending order, so I need to reverse it. Then I will take the first two elements of that list, and then I will sum it. And basically, this program will actually do what I want. So the question is, how can we actually find this in an automated way? So we actually often see programs as trees, as abstract syntax trees, where, since again, we don't have conditionals or loops, so it's a bit easier to express them. So you can just think, okay, like that problem there is the same as having this tree. Where at the root level, you have the output of your program, and on the leaf levels, you have the input of your program. So the idea is, again, we're doing a tree exploration, and to try to find the correct label to each node until we have a full program, right?
One question.
Yeah.
Are you going to find small problem?
Not with our approach, yes. Well, yes. I mean, depending on what you do for. Like, so it's often the case that most synthesizers, what I did in the past was that I asked the question, can I find a problem, let's say, of one line of code? And then I iterate. And then I try 2 lines of code and so on and so forth. But if you say, okay, my search space is a tree of depth k, and I'm going to search on this tree, then it will not be guaranteed that you will find the smallest program. Yeah. So it really depends. Another important aspect would be that there's this notion of partial program. So partial program is there are some nodes that have question marks. So I still need to branch on them to decide what I'm going to pick there. So you can think this is a kind of like SAT solving, but instead of just being 0 and 1, I have multiple label for each node. So it's more like CSP style, I guess. OK, so how do I do this? So what is my search engine? So I need to choose a variable, right? So that's the goal. So at each node, I need to pick something. So here I'm not using the VSIDS heuristic or anything like that. So we're actually trying to use machine learning because other people have done this in the past. So this is not something I propose. It's just I'm just trying to reuse and showing that if you build upon the machine learning aspect, maybe you can actually improve those results. But again, you could replace this with any heuristic that you want. So the idea is, OK, maybe I can train a neural network over input-output examples. And here you can see we have some integers. They're all smaller than the output. At some point, I need to choose something that make numbers go larger, right? Because otherwise, I will never get 158. So maybe the machine learning will tell me, well, try some. Because you also know that this has to return an integer, so there's some type constraints that you need to obey. So you have to ask the machine learning, give me something that returns an integer. And OK, maybe sum is the best option, right? Maybe not. So it's a stochastic process, of course. And then you repeat this until you actually have a full program, right? Once you have a full program, you can run your input-output example. And then if it passes all your input-output examples, you say, great, I found my program. If not, you backtrack chronologically, and then you try again. So you're just doing a DFS search over tree space. The only difference is that you're guiding the search using machine learning algorithm. So what is the big downside of this is that I only know if I got it right or wrong once I have a full program, right? Because only once I have a full program, I can actually run it on my input-output examples. So can we do better? Like, can we actually backtrack when I know that it's going to be impossible to find a program, even though I still have some holes? So can I do this partial programming in check conflict? So can I do something similar to unipropagation? That was the hope here. So we have something there, but to do that, we need to augment our system a tiny bit, right? So we need to have some logical specifications so that we can actually propagate some information. And to do that, we introduce this notion of imprecise specification. So the idea is, OK, I have these components, let's say take, filter, etc., and they do something. But I don't want to precisely describe what they do because it may be very hard for me to actually, or maybe like a quantified formula, and then it will be very hard to reason about that. So instead of precisely describing the component, which can be challenging, I'm going to use simple properties. So the idea is that I'm going to use, let's say, if it's lists, I'm just going to reason about what happens after I apply the operator in terms of the size of the list and the maximum element of the list. And this is very imprecise and it's a large approximation. But it will allow us to actually do something with it. And this is kind of easy to write. So the filter, I could just say, well, I'm doing some filter, but I don't know anything about the predicate t, but I just say, okay, after I apply filter, I know that my list is going to be the same size or it's going to be smaller. And the maximum is going to be the same or smaller. So it's kind of like very, very imprecise specification and very easy to write. I'm just using linear arithmetic here, but of course you can use other things as well. And you do the same for the other components, for take and for head, right? So for take, you also just say that the size is going to be the same or smaller. Actually, you actually know the size of the list is going to be exactly the same, the value that you put there, because you're getting a sublist of the first n elements, and the maximum value is the same. And for head, you just say, well, the element I got is guaranteed to be smaller or equal than the maximum. So the only thing that is important here is that the specifications need to be true, right? Because we're going to reason about them. So if they're not valid throughout all your programs, then you have issues, right?
It's the user who provides the specifications, like augmentation of your language.
Yeah, so in this case, I actually wrote the specification myself, but the idea is that if you're the user, this should be easy for you to write. If you wanted to, because like, I'm going to show you examples over lists, but let's say you want to do tables or strings or bit vectors or something like that you want to reason about, you should be able to write it your own specifications.
Well, you would have libraries with specifications, right?
I guess you could have as well, yeah. So, and we didn't actually like do much improvement over this was kind of like the basic things we wrote. We didn't optimize over the specifications, but they're kind of important actually. So there's a lot of work that could be improved here. But the idea was that they should be easy to write so that people can use them. And they're not too expensive also to reason automatically, right? So if you have quantifiers, then you may have some problems afterwards. Because now I'm going to show you how can we use the specifications to actually backtrack earlier. So the idea here is, let's say we are in this state. So we have this partial program, and there's some holes here that we don't know. And now what I can do is I can write this constraint system that is basically, I'm just writing the specification for each node and conjoining them with, of course, variable substitution for the input-output, right? So now I know that if this system is not satisfiable, it doesn't matter what I put here. There's no solution for a completion of this partial program. If it's satisfiable, there may be a completion that will actually lead to the solution. And in this case, the reason why it's unsatisfiable is because of this constraint highlighted in red, which is actually the core. So in this case, I actually throw this to the SMT solver, let's say Z3, and then Z3 can give you the core rights. And the idea is that if you notice, all the elements I pick here, of course, it's very artificial, they all either decrease or maintain the maximum. But I know that at the end, I have to have a large value, right? So I need to have, at some point in time, one component at least that will increase the maximum, right? So because of that, you have this conflict. So the good news here is, this is great, because a partial program actually represents many complete programs. So I can actually backtrack earlier, right? Kind of like the bad news is that, okay, I'm still only pruning this part of the search space. So the question was, can we prune other parts of the search space at the same time by doing some sort of learning? So the question was, okay, can I find another equivalent partial program to this one that actually has the same issue of this one? So how can we actually learn from conflicts? Okay, so the goal was to learn from equivalent conflicts, and we introduced this notion of like two components, or let's say two functions are equivalent. If at a given node, let's say n1, I could replace take by this other function, and I have the same issue, right? And I'll give you an example about that. So we have the constraint system, and now let's focus on take. And now the inside core is important because the reason of accessibility, even though take may have a long description, is just because of this line, right? So that means that if I have another component that has the same property that maximum does not increase, I have the same issue, right? So that means that now, if I have other components like sort, reverse, and filter, I could replace this node by, let's say, sort and reverse and filter, and all of them have the same issue. So none of these partial problems actually will work. So that means, of course, if you want to detect this, you could do an implication check. Since our domain is actually bounded, we can even do this offline computation for all possible combinations of all possible constraints in the specification. And then online, you can actually just check, okay, like, tell me what is the equivalent class of this component with respect to this only one constraint, right? So this is great because now, in one step, I can actually cut a lot of equivalent infeasible programs in some sense. And if you do the same idea for all the other nodes, then you can actually cut 63 other partial programs. So in one step, you're actually cutting a lot of partial programs, and we're avoiding a lot of mistakes in the future. So just a quick recap. So this is just, we're doing kind of like conflict-driven. Like we're searching. We have a partial program. We're checking if there's a conflict. If there's no conflict, we search again, kind of like side solving. Once we have a conflict, we learn it. We're using this equivalent model conflict that I described before. And we do this until we either have no solution or we find a synthesized program. Right. So let me show you some results to see what is the impact of each of these techniques. So we compare against DeepCoder and this list domain. And in the paper, there's more experimental results on table domains as well. So in particular, DeepCoder was done at Microsoft Research in Cambridge. It's not publicly available, but we had like close contact with authors to try to faithfully implement it. But the idea is that even if our implementation is not the best, like how would these things improve upon the baseline, right? And then we have 100 challenging benchmarks that do this list operations. So here on the x-axis, I have time in seconds. So we have a timeout of 300 seconds, so only 5 minutes. Then here we have the percentage of benchmarks solved within that time frame on the y-axis. So our baseline would be just doing enumeration. So here I'm just doing a differ search until I find the full program, then I run it, and then if you pass all output examples, I stop. If not, I backtrack and try again. Just to see how that will behave, right? Again, everything is implemented in Java, so performance is not the top concern right now, right? It's just a prototype and an idea. So here we show that we can solve around 20% of the benchmarks within 300 seconds. The way to interpret this plot, it's not the kind of plot, it's a bit different, but it's kind of similar. So you can think about if you put the timeout on 60 seconds, then you can see what is the percentage of benchmarks that you can solve. So in some sense, you can see the improvements over time in terms of how many benchmarks you can solve. So it's a different way of seeing it. So if I do machine learning on top of this, so I'm now using machine learning algorithm, not ours, but whatever they did, like just to see how you can improve by guiding the search. So as you can see, there's actually a real improvement by using machine learning, which is great. And now, if you use this logical deduction to prune the search space with these partial programs, right, by using the imprecise specifications, we can see that now, I'm not sure if this is very visible, but we can solve around close to 60%. And here there's an interesting behavior that for a lot of benchmarks, actually it is worse to use this partial pruning than not, right? And the reason is at each check, at each step, I'm actually calling SNT solver and checking is this partial program correct or not, which is very expensive, right? So maybe you want to have an heuristic that only do this once in a while. We didn't really optimize the framework. But so I'm just saying, yeah, there could be improvements. Maybe you don't want to do this all the time, right? Because, I mean, we don't do it all. There are some constraints when it's hopefully to do it, and we have that. So you need to have a path between the input and the output so the information propagates. So before you have this path, it doesn't matter if you call it or not, it's always going to be satisfiable, right? And another problem here is that if it's the SNT solver says satisfiable, we're actually not using this information, right? So there's a lot of calls that are kind of wasted, right? But still we can improve. With learning, so this is like everything up together. So it's if you improve it, putting learning on top, then we can see that we can actually solve much more and much faster, right? So even though we have the same problems, right? Because now we actually can cut the search space by a lot. So I think it's really exciting news because it's the first time this has been done in synthesis, at least with this type of learning.
So the learning in this case, you have machine learning, which is just the statistical thing.
Yeah. So this
learning is the closed learning.
Yeah. Okay. The two learnings which can be confusing. Yes. So this is machine learning. This is, let's say, logical learning. Maybe it would be better. Yeah.
All of them generalize the same way, or some of them are better at generalizing?
What do you mean by generalizing?
Try more examples. Try different, because you give a few examples, you get the program.
Yeah.
Right?
We didn't actually check if they generalize better for other examples or not.
Yeah, well, I mean, when the quality
But
of what you are...
The program you're finding.
Yes.
Yeah, usually the program is actually the same or very similar. I mean, you can actually, there can be more than one program that actually work, and both of them are correct. So I actually look at the programs to see how different they were. I would say 90% of the cases they're actually the same. Sometimes they differ, but they seem okay for the input-output examples that were provided. But that was not what I was trying to solve. I mean, I think that was a different... here I was just trying to see, can logic put in the search space more efficiently? Of course, generalization is another problem that should be solved as well.
Do you have an overfitting problem? You have this bunch of examples and you try to build the program that correctly works with these examples. So do you somehow try to address overfitting?
No, there's no, again, like, to be honest, like in this work, we're mostly focused on can we cut the search space, right? So it's true that your program is only guaranteed to work on those 5 problems, right? And nothing else in theory, right? And to be honest, like even for this deep coder, they randomly generate a lot of programs. So for the table domain, actually our programs come from Stack Overflow, from real questions. But here, this ones, they actually came from random generation from Microsoft Research. So like they actually don't really have a concrete meaning, kind of like. It's hard to know, is this the right program or not? Because I don't even know what is the right program means, right? But yeah.
Yet you only learn for one run and then you forget it. But as far as I understand it, your propagation rule are also kind of incomplete, isn't it? And could be, for example, pre-processing, you deeply think about your system creates now new pre-processing rules or checks it now on the next example, finds this new logical tuning rule will do better, so exactly how to do
I think that could be a good, yeah. So in each case, like each benchmark, we learn and forget, yeah. But it's true that you could learn across benchmarks, right? But that we did not do yet, yeah. That could be something interesting. So yeah, just conclusion. So this is the framework. Uses cool stuff. Just some caveat for here. As you guys can see, like okay, we present this as a CDL style of solver, but you can think about it's kind of like a Seeger style or a Segi style of approach, right? Where you have a counterexample and you do some refinement. And I think the big difference is like we're trying to do like this kind of generalization of counterexample, even though there are different generalization of counterexamples done in Seeger and in Segis as well. But I think this is a bit different there. And you can think of, you're kind of like solving SMT solving as well, right? This is like a special theory that you're using. I guess the main difference there is every time we do this propagation is actually a different formula. So on the SMT solver side, this formula is actually built from scratch every time, right? But on the SAT solver side, where we actually learn and we have the tree information, that just grows, right? Until you do until you clean the database and so on, which is not very good right now. So this is like very, very preliminary work. And something that also I was thinking earlier this week that we had this talks about symmetries, and maybe actually the learning we're doing here is not really the learning of SAT solvers, right? But maybe it's actually just a symmetry breaking learning. Because like I have this problem, doesn't work, maybe we're actually doing symmetry breaking. So I didn't think about this before, but maybe there's some connection there. So maybe there's something to think about. Like this is a different type of learning, which I realize, I agree that this is much weaker than what CDCL solvers are doing, right? And of course the idea is that SAT solving has been great, right? It changed the world, and we now can solve millions of variables, etc. And program synthesis, the real reality is that we can synthesize programs that have like 5 to 10 lines of code, right? Which is not that great in terms of like complexity. Can we actually like have more sophisticated learning that actually will allow us like in 5 years to learn 100 lines of code or 1,000 or even more, right? So that's the takeaway message. Well, thank you very much for
So one thing you seem to be doing is